the behavior of holomorphic functions around its isolated singularities a bit further. In this lecture, we will state and prove the residue theorem. Residue theorem broadly answers the following question. Suppose you have a function f which is holomorphic on an open set omega minus a set capital S, where capital S is a set of singularities, a discrete set of singularities. Then what can we say about the integral of f over gamma, where gamma is some curve in some closed curve in omega minus s, basically a curve which doesn't pass through any of the points of singularities. If you think about it carefully, if capital S was empty and if our curve gamma was null homotopic, this is just the Cauchys theorem. The Cauchys theorem tells us that this integral is equal to 0. So in some sense, the residue theorem can be thought of as a generalization of the Cauchys theorem. However, the presence of these singularities makes the answer to this question a bit more complicated, and we will be answering that question in this lecture. Let me begin by defining the residue of a function at a point z0. So let me start by the definition of residue of a function at a point z0, at a singularity basically. The residue will be interesting only at singularities, in fact non-removable singularities to be more precise. Let f from omega minus s into c be a holomorphic function. Let me set the premise for you, where omega is an open set and S is a discrete subset of omega. So notice that discrete ensures that each point of capital S is going to be an isolated singularity. Discrete basically means that if z0 is in capital S, then there exists some r such that d z0 r intersected with S is just the set z0. No other point of S will be in that particular neighborhood. So suppose we have a discrete subset. Then for z0 in capital S, let dz0 r be, let r positive be such that dz0 r bar is contained in omega and dz0 r intersected with capital S is the set is z0. This is possible because our set capital S is discrete. Then I should start with then for z0, let this be the disk we are interested in. Then in dz0 r minus z0, in this annulus, the punctured disk of radius r around z0, consider the Lorentz series expansion, of f given by f of z is equal to summation n is equal to minus infinity to infinity an z minus z0 to the power n. So suppose we consider this disk, and in this disk we will have a power series expansion, or rather Lorentz series expansion of f in this manner. We define the residue of f at the point z0 to be the coefficient of 1 by z minus z0. The coefficient of 1 by z minus z0 is special. Let me note it down. We define the residue of f at z0 to be a residue. This is the notation, residue of f at z0. This is the notation. This is going to be defined as a minus 1. Remember that the moment we fixed such a annulus, we have a Lorentz series expansion, and And in the given annulus, this Lorentz series is unique, and we even know exactly how to get hold of our coefficients through the relevant integrals. So this definition makes sense, even though it's a local definition, it certainly makes sense. And the coefficient a minus 1 is called the residue of f at the point z0. Let's look at a few cases rather than examples here. If z0 is a removable singularity, notice that z0 is just some point in capital S, it's hence just some isolated singularity, and therefore it could be a removable singularity, it could be a pole, it could also be an essential singularity. Let's see what happens when it is a removable singularity. If z0 is a removable singularity, then by the classification theorem using the Lorentz series, what do we have? Then a minus n is equal to 0 for all n in natural numbers. All positive integers n, you look at a minus n, that's going to be 0. That's the characterization of removable singularities using the Lorentz series. And that tells us in particular that a minus 1 is 0, and hence the residue of f at z0 is equal to 0. So in particular, what is a removable singularity? A removable singularity is a singularity over which we can extend our function holomorphically. So in some sense, the removable singularity behaves like any other point where our function is holomorphic, and hence the residue there is going to be like any other point in the domain where it is indeed holomorphic. The residue at points where it is holomorphic is being put as 0. That's what this basically means. Let's look at when z0 is a pole. So if z0 is a pole of f, what happens if z0 is a simple pole, order 1, pole of order 1? Let's first consider this case of order 1. That means that f of z is equal to g of z by z minus z0 in dz0 r minus z0, where g does not vanish. In this set dz0 r minus z0, if you want to shrink it further, you can, and finally assume that g does not vanish in this neighborhood at all by using the continuity of g. G of z0 is not equal to 0 will be something which we have. That's what is used to conclude that g will not vanish here by shrinking. But anyway, the point is that this tells us that z minus z0, and we even have the explicit Lorentz series expansion. F of z will be something like a. Okay, let's see. This is going to be equal to z minus z0 is just going to be equal to a0 plus a1 z minus z0 and so on, and therefore f of z is just going to be equal to a0 by z minus z0 plus a1 and so on the punctured disk. And this tells us that the residue of f at the point z0 is exactly equal to a0. But what was that? That was exactly equal to g of z0, which is not equal to 0, right? In fact, we could generalize this idea to an arbitrary order. In fact, if z0 is a pole of some order, say m, then what will happen? Then we could write f of z as being equal to z minus, maybe I'll just skip a few steps, directly write this to be z minus z0 to the power m times g of times f of z is equal to g of z, where g has a removable singularity at z0, and after extending, g of z0 is not equal to 0. In fact, g of z we will assume is not equal to 0 on dz0 r minus z0. Suppose this is what g is going to behave like. Then what do we have? Then the Lorentz series expansion of f, this is going to be equal to a0 by z minus z0 to the power m plus all the way up to a m minus 1 by z minus z0 plus am and the remaining part. And therefore, the residue of f at the point z0 here, this is just going to be equal to am minus 1. What was ai's here? Where g of z was equal to summation an z minus z0 to the power n. That was what was used to conclude that the residue of f at the point z0 is am minus 1. But we also know what is am minus 1 in terms of g, isn't it? This is just g m minus 1 of z0 by m minus 1 factorial. Therefore, we can actually conclude the residue of f at z0 as being equal to 1 by m minus 1 factorial times the m minus 1th derivative of g at z0. In the case of essential singularity, we don't have any easy way of concluding any of this. We will have to get down to maybe the Lorentz series expansion and look at what the coefficient of 1 by z minus z0 is. Alright, now that we have seen what the residue is, let me now state the residue theorem and we will then give a proof of the residue theorem. The residue theorem. The setup is going to be the same. Let omega be an open subset of C and S. Let's put the restriction of finiteness on S, be a finite subset of omega. So I'd like to remark that we don't need to impose the stronger condition of S being a finite subset. S being discrete actually is more than enough to conclude this theorem, but we will then have to use a stronger machinery called the Jordan curve theorem to conclude what we are concluding for the case when S is finite. So let me avoid the reference to the stronger unproved theorems by putting this restriction here. So let omega now be an open subset of C with a finite subset capital S. And suppose f be a function which is defined on omega minus S and is holomorphic there. Let's take a curve gamma which is both a closed curve and which is null homotopic in omega. Let gamma be a null homotopic closed curve in omega, not in omega minus S, we are demanding that it is in omega. Then the integral of 1 by 2 pi I f of z dz over gamma summation w gamma of zj, where w gamma is the winding number of gamma around zj times the residue of f at the point zj. And what are the zj's? Zj's, the summation is from j equal to 1 to n, where capital S is the finite set given by z1 to zn. Maybe I should use a k here. Zk. So there are finitely many points as was observed earlier. So let me enumerate them as z1, z2 to zk, and w gamma is the winding number. Okay, so let me just go over the proposal, the theorem for you. We are considering a function f which is holomorphic on omega minus s, where s is a set of singularities, isolated singularities. And if you look at the integral of f of dz over gamma, that's going to be equal to 2 pi I times the thing on the right, which is basically the sum of w gamma of zj times the residue of f at zj. So if you notice, the residue is coming into the story in a very natural manner here. Let's give a proof of the residue theorem here. We'll begin by defining a function g by capturing the residues of f at the various points zj's. So define g of z to be equal, what is g of z equal to? G of z is equal to summation the residue of f at the point zj by z minus zj, again where j is from 1 to n. If you notice, g is also a function which is holomorphic away from zj. So notice that g is holomorphic on omega minus capital S, just like our small f. Moreover, if you look at g of z, let's focus on zj, fix zj and dzj r, and r positively such that dzj r bar is contained in omega and dzj r intersected with S is just the point zj. Suppose we have picked the right neighborhood around zj because it's an isolated singularity, and we will be able to write our g of zj as the residue of f at the point zj by z minus zj plus the remaining terms which I will capture with g1 of z. And the observation here will be that then g1 is a function which has a removable singularity at zj. In fact, I will safely write it as being holomorphic on dzjr. And therefore, if you look at the residue of g at the point, say zj, that's going to be equal to exactly the residue of f at the point zj. Why does g1 have holomorphic expansion here? Why is g1 holomorphic here? That is because if you notice this term, there is only one by z minus zj term that appears. In dzjr, no other singularity point in capital S appears, and therefore this function is very safe that it's a holomorphic function, that whatever remains after taking out the residue of f at the point zj by z minus zj from the expansion here, everything else is going to be holomorphic. Right. So if you now write down the power series expansion of g1 and look at the definition of the residue, we get to conclude that the residue of g is the same as the residue of z. Now further define capital F of z to be equal to f of z minus g of z. Now what is the good thing about our function capital F? Let's assume that the integral of capital F is 0. Let's assume that if the integral of capital F over gamma is equal to 0, suppose we manage to prove this, then that would imply that the integral of f minus g of z dz over gamma is equal to 0, isn't it? And that would imply that the integral 1 by 2 pi I times the integral of f of z dz, this is exactly equal to 1 by 2 pi I times the integral over gamma of g of z dz. But computing the integral of g of z dz is quite straightforward, because this is exactly the sum of the residues of f at zj by z minus zj. This is precisely what our function g is going to be, isn't it? And this is again by the very definition residue of f at the point zj. Notice that they are constants times, this is the sum of this times the integral over gamma, more than that it's 1 by 2 pi I times the integral over gamma dz by z minus zj, where j is going from 1 to n. And that's precisely whatever is written down in the brackets is exactly the winding number. This is w gamma of zj times the residue of f at zj, and we would have completed the proof. So the only thing to establish hence would be the thing which is put in the box here, or maybe this box. So the only thing that we need to conclude is that the integral of capital F is equal to 0. Let's try proving that. To venture into proving that, let's try to first see how the Lorentz series expansion of f turns out to be. Notice that since f of z is equal to f of z minus g of z, we already have a Lorentz series expansion of f around z0, around zj, right? So since this is the case, in a neighborhood dzj are around zj as above, that means that, okay, maybe I should be around zj such that dzj are intersected with s is just zj. It's a small enough neighborhood that it intersects only at the point zj, and dzj bar is contained in omega. So take one such, and there we have a Lorentz series expansion of f as well as g, isn't it? We know exactly how the Lorentz series expansion of g is going to be. Let me just write down. Then f of z is going to be equal to some summation an z minus zj to the power n. Over there we don't know what type of a singularity it is, so let me just put the Lorentz series expansion this way. And g of z, we know exactly what the singularity is. It's going to be a simple pole at zj. It has a pole of order 1 at zj. So this is going to be residue of f at zj by z minus zj plus whatever remains is some g1, which is a holomorphic function there, which I will write it as bn z minus zj to the power n. So this is precisely what we have. So on the disk, on the punctured disk, this is all on the punctured disk, and the convergence is absolute here, so the terms can be added, and we will be able to hence conclude that capital F of z is going to be equal to summation n is equal to 2 to infinity. Notice that the residue here is exactly equal to a minus 1, which features here. So the sum will tell the difference, rather fz minus gz is going to be the sum of a minus n z minus zj to the power minus n plus summation, let me put up prime to denote that it is something like an plus bn from 0 to infinity of z minus zj to the power n. And notice that this is an absolutely convergent series, and the Lorentz series expansion is unique, and this tells us that this is the Lorentz series expansion of capital F on the punctured disk. Let's now define the fact that there is no n equal to 1 in this summation is of great advantage to us, because we can explicitly write down an antiderivative of capital F on this punctured disk. Then on dzj r minus zj, consider g of z to be defined in the following manner: n equal to 2 to infinity a minus n z minus zj to the power minus of n plus 1 by minus of n plus 1. Notice how crucially we are using the fact that the n equal to 1 term doesn't feature here, and the second term anyway is fine. That's going to be a n prime z minus zj to the power n plus 1 by n plus 1. If you consider this particular function, then I will leave it as an exercise for you to sit down and check that this is also absolutely convergent. By using the fact that capital F is absolutely convergent and doing a comparison, you can conclude that on this punctured disk, capital G is also absolutely convergent. And for any Z, by picking a smaller annuli of R1 and R2, where say 0 is less than R1 and R2 is less than R, and such that R1 is less than R2 and Z is in the annulus of R1, R2, the uniform convergent tells us that G prime of Z is exactly equal to F prime of Z. We can differentiate it term by term to get back function capital F here. So in other words, notice that on the punctured disk, capital G is a holomorphic function, and therefore in dzj r minus zj, f has an antiderivative. And that is good, because if you now take any closed curve in dzj r minus zj, hence if C is a closed curve in dzj r minus zj. Notice that I have slowly stopped using the word rectifiable, because I am now talking about the integrals up to homotopy thanks to Cauchys theorem. What do we get to conclude here? By the second fundamental theorem of calculus, we have the integral of f over c is equal to 0. In fact, these are at the points of singularities. In the punctured disks around Zj is what we are considering our integral of f over c. The other case, if Z does not belong to, or rather it belongs to omega minus capital S, then let R positive be such that dzr bar is contained in omega and dzr intersected with S is empty. So you can always get hold of a small disk of radius r around Z which satisfies these conditions. Then by Cauchys theorem, this is a simply connected domain, and hence any simple closed curve is null homotopic, and therefore by Cauchys theorem, integral of f over c is equal to 0 for every closed curve in dzr. So what we have essentially established is that irrespective of which point we pick in omega, whether it is in S or whether it is in omega minus S, we can either get hold of a punctured disk or we can get hold of a disk, such that the integral of f over any closed curve in the respective neighborhood is going to be 0 of our function capital F. This is a very important observation. So let me just put a star and a star star for the purpose of finishing the proof. Okay, so with this observation at the back of our head, let's try to now prove that the integral of f over a curve gamma is 0. So let gamma from a b to omega minus s be null homotopic. What does it mean to say that it is null homotopic? It means that i.e. there exists capital H from 0 1 cross AB to omega. So this is null homotopic in omega. Remember that the statement of the theorem only demanded that our curve be null homotopic in omega. Oh, I didn't mention that. It is mentioned as closed curves in omega. So the homotopy is in omega. So let's take a homotopy capital H so into omega. So that's precisely what it means. There is a continuous function such that h0 comma or such that gamma 0 is equal to gamma and gamma 1 I'm just using our notation from earlier. This is some gamma z naught, where gamma z naught of t is equal to z naught for all t in AB. So we end up with a constant curve at some point z naught. That's what it means. And where gamma s is, and such that gamma s is a closed curve for every s in 0, 1. So this is precisely what it means for our curve gamma to be null homotropic. Now, 0, 1 cross omega is a compact subset of R2, right? Since 0, 1 cross omega, not omega, AB is compact, so is h of 0, 1 cross omega. Because continuous functions preserve the property of being compact. So this is going to be a compact subset in omega. And we consider the cover U prime, let U prime be the cover of all the neighborhoods as above. This is going to be the collection of all dz or z maybe, such that z does not belong to capital S, dz or z bar is contained in omega, and dz or z intersected with S is empty. Notice that this is the exact collection of neighborhoods where our capital F had the property that its integral over any closed curve is 0. So we will take the union of this with what happens when it is in S. So this is not in S, I'll just change it to, I'll just put Z in H of 0, 1 cross AB minus S. I don't want for every point in omega, it's just in the image that we will consider. Union the collection of all dzj, rzj, such that zj 1 is less than or equal to j is less than or equal to k, dzj R, maybe I'll just put an Rj here, Rj bar intersected with S is the set Zj, and dzj R j bar, maybe I'll put this extra assumption that the points in S doesn't belong to the closure. That can also be arranged, right? It's just going down to a smaller set if needed. So this is the exact collection. So I have not done, even though I have written it in this manner, not done anything new. I have just captured those neighborhoods where star and star star are being satisfied. If you go up and check, that is precisely the collection that is being considered. And this is going to be an open cover of H of 0, 1 cross AB, because we are doing this for every point there. Where this is the case, and Zj belongs to capital S. If Zj belongs to H of 0, 1 cross AB. If it is not in the image, we will not be interested. Let's only consider those points in the image of H, under image of 0, 1 cross AB under H. Right. So being compact, by compactness, we get a finite subcover. Let U, which I will denote it by U1 to UN, let me not try singling it out, be a finite subcover. And further, because this is a cover of our image of 0, 1 cross AB under H, there exists a Lebesgue number. We will denote that Lebesgue number by epsilon. Okay, subcover, and let epsilon be the Lebesgue number corresponding to U. Now, what is the good thing about U? If you take any closed curve in U1 or any closed curve in U1, U2 up to Un, which is not going through the point of singularity, if it is around a singularity, then the integral of capital F over C is going to be 0. That's precisely what star and star star above had ensured. We are going to use that, and the fact that our H is a continuous function on a compact set implies that it's uniformly continuous will be used to get hold of a partition of 0, 1 cross AB. Let me just note what I just said. By uniform continuity, so if you recall the proof of Cauchys theorem that we proved some time back, you will notice that we are actually going down the same rabbit hole. It's not very different. The proof is actually mimicking the proof there, but we have to be a little careful about the singularities. That's precisely what we'll be doing. By uniform continuity, there exists a delta positive such that the absolute value of h of s t minus h of s prime t prime, this absolute value is less than say epsilon by 4 whenever absolute value of s minus s prime is less than delta and absolute value of t minus t prime is less than delta. If both these conditions are satisfied, we can ensure that h of s comma t minus h of s prime comma t prime is less than epsilon by 4. Okay, let's now, as I was mentioning, let's now mimic the proof of Cauchys theorem. Let's get hold of a partition of 0, 1 and AB. Consider the partitions. Zero equal to S0 less than S1 up to say Sn, which is equal to 1, and A equal to T0 less than T1 less than up to Tn equal to B, such that the partition size in both the cases is less than delta, thereby ensuring that h of Si Tj minus h of Si minus 1 Tj is less than epsilon by 4. That is being ensured, or for that matter the other variable as well. But not just that, we also demand a little more. So let me just draw a picture before describing the other demand. So suppose we have a closed curve of this type. So suppose this is the point Z0, and I'm going to draw the SJs using different colors. So let me use red to draw some S1, pink is to draw maybe green, light green is to draw S2, and violet is to draw S3. I cannot draw more closed curves in a clean manner, so let me stop there. Let me use orange to capture TJs. We have TJs, so we have partitioned our SJs and SIs and TJs in this manner, and what our demand will be is the following. You look at the blue polygonal paths. So this is the arrow. Our demand will be that if you take any such polygonal path, it will not have a point of the singularity. Notice that because our set of singularities is finite, by perturbing Sj's and Tj's, if needed, we can always ensure this. So let me just note what I just said, such that for every I comma j, such that one is one is less than or equal to I is less than or equal to n, and 1 is less than or equal to j is less than or equal to m. If you look at gamma Cij, which is gamma polygonal path Sitj, this is Sitj coming down to Sitj minus 1, going then to Si minus 1, Tj minus 1, then going up to Hsi minus 1 Tj, and then going back to Sitj. If you look at this polygonal path does not intersect capital S. So, in none of these polygonal paths do we have any point of our singularity. That is what is being ensured by the partition. So, we were picking a partition. Remember that we were trying to get hold of a partition here. The partition had the following properties. Let me repeat the properties. It has the mesh size or the partition size less than delta. The delta was corresponding to the epsilon that we picked here, and further that if needed you can perturb Sj's and Ti's so that none of the Cj's have any point of Cij's have any point of capital S. This much we can always ensure. And once we have this, recall by a similar argument as given in Cauchys theorem, we get to conclude that the integral of, so if the integral of f over Cij is equal to 0 for all I comma j, then the integral of f over gamma 0 minus the integral of f over gamma 1 is just going to be equal to the sum of the integral of f over Cij, where I is going from 1 to n and j is going from 1 to m. Further, each of this is going to be equal to 0. Oh, that we have not concluded. This is precisely what we get to conclude. We are going to now conclude. Let me write down the claim. Oh, what was gamma 0 here? Gamma 0 was just gamma, and gamma 1 is just gamma z0, the constant curve. So, we will come back to this. Let me call this star star, or let me not call it anything. The claim is to show that integral of Cij of f of z dz is equal to 0 for all I comma j. Now, we have done all the hard work here, because if you notice that the arc length of Cij is going to be less than epsilon. Further, which tells us that the diameter of Cij hat, the convex hull, that's also going to be less than epsilon, which tells us that Cij hat is contained in some u for some u in script u. What was script u? Let me just go up and show you what script u was. Script u was a finite subcover such that if you look at any closed curve in this manner or any closed curve in this manner, the integral of f over that closed curve is 0. It's precisely how we picked our script u, isn't it? And the fact that we perturbed our Sj's if needed to ensure that it doesn't intersect capital S, these curves Cij's don't intersect capital S, the precautions was taken in order to conclude that the integral of f over Cij is going to be 0. By star, let me put it this way, by star and star star and the fact that Cij does not intersect capital S, we can hence implement star star if needed, and we get to conclude that the integral of f over Cij is 0. But then let's go up here and let's look at the equation that I have just underlined in green. The right hand side is the sum of the integral of f over all Cij's, and let me now put a star 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 here to refer it below. Hence by star 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 we have the integral of f over gamma is the same as the integral over gamma z naught, which is the constant path, which is equal to 0. And that's precisely what we were trying to conclude. So let me note here that we have just established that the integral of small f is the same as the integral of capital F, and we had given what happens when this is equal to 0, isn't it? We had noticed that then the integral of f over gamma 1 by 2 pi I times that is exactly equal to this, which we were expected to conclude.